Okay, so this question is on the photoelectric effect, and the first part is saying when monochromatic light, that's light of one wavelength, is incident on a metal plate, electrons are emitted. So instantly we can say that the energy of the photon is going to be greater or equal to the work function of the metal. If photoelectrons are emitted, that is the case. The intensity of the light is then increased, and the question wants to know, why does the maximum kinetic energy of the electrons not change? Well, the reason for that is that the intensity is just the number of photons per second. And that means that the energy of a photon does not depend on intensity. Therefore, the electrons do not have more energy. The next part says why the number of electrons emitted per second increases. Well, if I increase the intensity, what I am doing is increase the number of photons per second. And since one electron can only absorb one photon, a higher intensity equals more electrons emitted. And if we want to be specific, we should say per second. The next thing is saying that a potassium metal plate is illuminated, and we have a wavelength of our light, and we have our work function. So show that the frequency of the light is approximately 6 times 10 to the 14 Hertz. Well, we want to know what the frequency is in order to prove that. We have a wavelength, and we know that the speed of light is 3 times 10 to the 8. And the easiest way to do this is just to use the wave equation C equals F lambda. Rearrange C equals F lambda gives us F equals C divided by our wavelength, and when we plug our numbers into that equation, 3 times 10 to the 8 divided by our wavelength, which was 5.1 times 10 to the minus 7, I get an answer of 5.88 times 10 to the 14 Hertz, which is approximately 6 times 10 to the 14 Hertz. The next part of the question wants us to calculate the energy in joules. Well, I know that my frequency, which I calculated beforehand, was 5.88 times 10 to the 14 Hertz. And I know what H is, so I can use E equals HF, plug my numbers in, 5.88 times 10 to the 14, stick some brackets around that, multiplied by my Planck's constant, my H, which is 6.63 times 10 to the minus 34. And when I plug those numbers into my equation, I get an energy for my photon of 3.9 times 10 to the minus 19 joules. Then it wants to know the maximum kinetic energy. Well, I know that if a photoelectron is emitted, then the energy of the photoelectron, or HF, or the energy of the incident photon, is going to be equal to the work function of the metal, the minimum energy required to release a photoelectron, plus the kinetic energy. Any extra energy left over from taking the work function away from the energy of the photon gives me the kinetic energy, or rather the maximum kinetic energy. Now I worked out the energy beforehand was 3.9 times 10 to the minus 19 joules. And we were given the work function, which was 3.58 times 10 to the minus 19. Now, if I want to be able to work out the kinetic energy, I need to rearrange this equation. And that gives me that kinetic energy is equal to HF, and I have to take the work function to the same side as HF, so instead of it being plus, it becomes minus. When I plug these new figures in, for this here being HF, and this here being the work function, I get an answer of 3.2 times 10 to the minus 20 joules. And that's my kinetic energy of the released photoelectron. Finally, I'm given 4 different metals with 4 different work functions, and I'm asked which of these would emit electrons when illuminated with light of this wavelength. So what I need to do is calculate the energy, HF, of the photon, which would be Planck's constant, multiplied by the frequency, but in this case we are given the wavelength, so I'm actually going to use the equation E equals hc over lambda. So I've got Planck's constant times the speed of light divide all of that by 5.1 times 10 to the minus 7, the wavelength of my light. And when I type that in, I get a work function of about an energy of about 3.1 times 10 to the minus 19 joules. Now the only metal with a work function lower than the energy of the photon, and therefore the only one for which that photon could release a photoelectron, is cesium.